Are there any questions from Monday? Any questions regarding the lecture on Monday? All right. Today we'll continue with object-oriented programming. In particular, we are going to look at these statically typed object-oriented languages. And I'll cover C++ today, the first part of C++. And then I'm not gonna, I'll have probably like a lecture for 60 or 65 minutes. And I have another meeting that I have to attend, so I'll not do the second hour, which is optional anyway. And we'll continue with the rest of the topic on Monday. Any questions? All right. So recall from Monday, when we talk about these purely dynamically typed object-oriented languages, specifically Smalltalk and Self, we mentioned quite a bit about inefficiencies, potential inefficiencies in the let's say in the runtime and in the runtime of or runtime performance of a program that is written with those with one of those languages. C++ kind of evolved around that specific idea, perhaps, and it's an extension of C. C is a imperative or procedural language, and C++ is actually just an extension of it, adding some sort of, let's say, an object-oriented concept into it. So this is, at the end of the day, you can consider C++ probably an object-oriented programming language, but with quite a bit of procedural, let's say, things in it as well. So it's not a purely object-oriented programming language from that perspective. And it was designed by, or C, if you recall, designed by Dennis Ritchie. And you can see some of the things, interesting things here. If you recall, so C is actually designed to write an operating system, Unix in specific. And it was used, it was based on something called BCPL. So, and we saw that actually Smalltalk was having very similar, let's say, motivation. Smalltalk was also a kind of a language as a user interface to a device, which is, in a way, it's, let's say, it's operating system. So there are a lot, I mean, you see this type of behavior quite a bit because, again, writing, let's say, an operating system requires, it's a big task, it's not a small amount of task, and it requires different things from a language that you would use to write it. And of course, one of the things that you can think about for writing, let's say, Unix or a kernel for an operating system, one of the things would be, first of all, you are close to the machine. So you need to be close to the machine. You are writing an abstraction layer. And that closeness, you are going to see that next semester, what an operating system is, if you haven't taken it already. But you need to actually put a layer between, or an abstraction layer between the programmer and the hardware. So it has to be close to hardware. So C is actually very, very close to hardware. It can, let's say, have quite a bit of things to do with the CPU, the memory, and so forth, and it has to be quite efficient, right? So, but in some other cases, maybe your efficiency need, especially like when we think about this Dynabook the other day, we talked about that LNK's idea. There, other things come into place, like you want to actually, let's say, have a modular thing that can be programmed and can be, let's say, manipulated by not necessarily an expert programmer, but let's say a casual programmer or non-programmer. So C was designed for that, and C++ was designed by Strastrup at Bell Labs. And the original interest was, again, simulation. So you see the parallels here. And then they actually, or he actually did the early extension to C using kind of Simula, based on Simula. He followed quite a bit of ideas from Simula in the beginning. So in early 80s, he called his, let's say, C++ or his language, C with classes, and then it actually evolved to C++. And popularity increased in late 80s and early 90s. So again, this has, of course, something to do with Smalltalk as well. People have seen advantages of Smalltalk or object-oriented programming languages, but efficiency issues were also a problem. Now you have this language somewhere in between that actually helps you to be efficient, and also it helps you to be actually, it helps you use these object-oriented programming paradigm. So I think this was a very, in the evolution of things in terms of this programming languages, this was a lucky, let's say, strike. And one of the things that you can also see that 1990s, early 90s, is when the internet starts kind of picking up, right? So the widespread programming was needed, and you cannot expect everyone to program everything in let's say in C. You need a little bit better language that helps us actually do larger things and with a larger number of people and so forth. And then features were added incrementally, classes, templates, and exceptions, multiple inheritance, type tests, and so forth. It is still being improved as far as I know. I am just going to talk about the basic original C++. So some of these slides might be old in terms of actually what is the current version doing and what I am claiming here. So the design goals for C++ were simple actually. So the basic idea was provide an object-oriented feature, right? So you want to provide an object-oriented feature to your language-based, C-based language without compromising efficiency. So you want to have object-oriented paradigm in there, programming paradigm in there, but you don't want to actually have it too inefficient. Again, so when you look at the things, what is happening in 80s, you have these personal computers are actually coming into play, right? So people before that, we had mainframes, and mainframes with, let's say, terminals connected to mainframes. And these were in, let's say, in the use was quite limited at universities, at banks, and some other research labs and so forth. But with the PC, you start seeing it getting into anywhere, including homes, right? But PCs are not as powerful as, let's say, your mainframes. They were very limited. If you think about, let's say, a PC, let's say state-of-art PC in late 80s, it was a 10 megahertz machine, like this Intel 8080, 8088. These were 10 megahertz. I mean, the speed, clock speed of the machine is 10 megahertz. Compared to today's clock speed is what? Usually, what do you see when you buy a simple PC, the simplest one? What will be the clock speed? Gigahertz, 2, 2.5, 3. So let's say 1.9 gigahertz, 2 gigahertz, or even 1 gigahertz. Is 1 gigahertz is actually how many times 10 megahertz? So you can see that actually the clock speed defines actually what you can do, and the memory, of course, also defines what you can do. And the memory is 640K kilobytes. What is a typical PC today in terms of RAM? 32, 8 gigabytes, minimum probably 8 gigabytes. You wouldn't buy something less than 8 gigabytes, right? I don't think if you look at, let's say, what is on the shelf today, probably that will come with a 16 gigabyte or whatever. This was 640 kilobytes. So from 640 kilobytes, now you need to still do things with that, and you could do things with those. You can play games, you can do some productive work and so forth. So the efficiency is a very, very big problem in those days. And you cannot actually just assume that you have a big mainframe that you can buy maybe, I don't know, paying tens of millions of dollars, and then you assume that you can actually use that for your everyday work. No, that's not possible. So efficiency is important. And another thing is also important, that you have a lot of C programmers. C was very powerful. C replaced many languages, including Fortran and COBOL and so forth. So C was the de facto language at the time. So if you want your language to be successful, the new language to be successful, maybe this was not intentionally so, but you need people to easily program with it, right? And if everybody knows C, and you better actually make sure that the C people can actually just convert easily to your language, right? So backward compatibility was one of the things that actually helped. I have some C code here, I can use them. And now that I have this new language, I can actually just use those code as it is and add on top of it. This is a nice, let's say, feature. And of course, this static type checking, this is better than C. So improving C's type checking mechanism would actually help because, again, you are having more and more programming things to do. And one of the problem is that development of program with C becomes kind of a cumbersome. So you need to trust, let's say, your libraries and so forth. And this is one way of actually helping there. So, and then, of course, these ideas, these nice ideas about data abstraction and objects and classes and so forth. And this last one is important, preferring efficiency of the compiled code over, let's say, anything else where possible is actually important, right? So compiled code tells you that things needs to be static, right? The efficiency. I don't want to have, let's say, runtime code for, let's say, doing dynamic lookup or, let's say, some sort of dynamic type checking, right? So the type checking has to be static if you prefer efficiency of the compiled code. Okay, Of course, this is important. We have been talking about this principle. If you do not use a feature, your compiled code should be as efficient as if the language did not include this feature. So this is something that that is important. Now we discussed this as this, if you recall, this orthogonality. We said, okay, if you have a feature, the other features should not actually should be orthogonal to the others. So I should not repeat the features in different ways, just a single thing. But here what we are saying is that if I have a feature that I don't want to use, so I don't know, for example, something I don't want to use, something I don't need. Maybe I don't need, let's say, lookup, dynamic lookup, or some sort of a lookup I don't need. In that case, I should be able to actually create a code that is actually not having the overhead of that feature because I haven't used that feature. So this is very nice. So if I don't use a feature which will come with an overhead, most probably, my compiled code should not include that overhead because I don't have that feature in my code. So this is important, and we are going to see this one, especially with this is one of the probably a design choice that is virtual versus non-virtual functions, and non-virtual functions being actually treated as C functions. In the compiled case, if you just go with the let's say all let's say regular functions, then that overhead is not going to be there at all. So this is nice. Okay. So the success of this language was quite good, right? So we know that. Given the design goals and the constraints, this is a very well-designed language because all these things that you want to have abstraction, you have to have, let's say, efficiency, you have to have, and you want to have encapsulation and classes and some sort of, let's say, typing mechanism around that, and perhaps also some inheritance mechanism that we are going to talk about. Then this is all these things, putting them together is kind of good. And the timing was right again. You have these low power machines, and you want to actually code in those machines. And this language actually has that property that you can actually help with these applications. All right. So it has many users, very popular, right? The design is quite complicated though. Many features with complex interactions, difficult to predict from basic principles. I mean, this is not a simple language. It's not an easy language to learn. And you know this one. You spent an entire semester almost, I believe, last year, right? So most users chose a subset of these language. So you don't, I mean, the programmers usually will actually, let's say, use a subset of it. I have seen C++, programs that has almost no object-oriented programming, let's say, paradigm features in it. Still a C++ program. And I have seen people using without, let's say, much regards to, let's say, inheritance, multiple inheritance, for example. Very, very few people use that because of the complexity and so forth. And also another problem with this one is implementation dependent features, properties are common to compilers. So this is a bad thing for a language. So I don't know what it is today. I'm not following it very closely, but in, let's say, 15 years ago, about 15 years ago, when we had, let's say, we had several compilers, and it was very, I mean, if you use a full feature of the language, it was very likely that one compiler's program will not run. I mean, one compiler will successfully run something, and the other compiler will not run it probably. Okay. So where does some constraints that comes from, first of all, the C, being an extension of C, because C has a specific machine model in mind. If you recall that, we discussed that. It has access to underlying architecture. Let's say the machine model, the instruction set that you have on machine, C actually follows that quite closely. So this is one constraint. So you cannot actually get out of this constraint easily, right? The other one is there is no garbage collection mechanism. Of course, the new editions I think have some garbage collected stuff in it, but the original one didn't have one. This is consistent with goal of efficiency, because garbage collection, if you recall, was a problem in terms of efficiency, but it was good to have because you can you don't need to actually explicitly manage memory, but that brings simply an efficiency issue, of course. So this need to manage object memory explicitly can create problems, right? So now you have a kind of a prone to bug feature that you have to actually be careful, and you have to rely on the programmer to have. Following the specific machine model, you have these local variables stored in activation records, as we discussed with Simula, right? So the objects treated as generalization of structs because of this, and objects may be allocated on stack and can be treated as L values, the left-hand side of the thing, if you recall. Now, because of that, you have this idea of actually stack versus heap thing has to be actually clear to the user. It has to be visible to the user. This difference, you have a difference between a stack and heap, and you have your programmer has to know about this. In Smalltalk or the other languages, we didn't actually have, we didn't even need to talk about memory management at all, because this was done automatically by the compiler. Now here, you need to actually understand which goes to stack and which goes to heap and so forth. The programmer needs to know about this. I mean, this is again coming from the constraint that we want to have the efficiency using these activation records, but at the same time, it brings about a difficulty of actually the need for understanding what heap is and what stack is. For a computer scientist, this is not a big problem, or a computer engineering, this is not a big problem. We need to know about those things anyway. But for a casual programmer, this is an issue. This thing has to be known, and if they don't know it, they will actually make probably mistakes along the way. So let's look at the object system of C++. With the knowledge that we have now, starting from Simula to Smalltalk and Self and JavaScript. So object-oriented features, we have classes. Now, as opposed to what we have seen the others are doing, like everything being an object, or we have some, let's say, distinction between a class and an object. This C++ actually takes the other way around. So C++ will be concerned with actually the programming of the objects or classes more than, let's say, the usage of those classes. Whereas, for example, Smalltalk will be interested, or Self will be interested more in the usage of the classes. So this is the true object-oriented thing, right? So I have some objects. I just want to actually manipulate those objects or talk to those objects to create an action. Here, again, this is coming from this original need from actually, you want to actually program everything, and you want to, especially, you are interested in programming the classes. Therefore, the perspective is going to be here from, we are going to make a lot of emphasis on inheritance, because again, C++ concerns itself with more with, let's say, how you build classes and how you actually interact with the other classes than how you build objects and actually interact with objects. And objects have some sort of dynamic lookup capability for some functions, not all functions, but virtual functions. You have inheritance, single and multiple inheritance is possible. Again, you see that typing comes later as a kind of a byproduct of inheritance. So the importance is here to pay to actually inheritance itself. And you have again, for the inheritance, you have the public and private classes that you can, let's say, it's a part of your inheritance mechanism. And subtyping, as I said, is tied directly to the inheritance mechanism. And of course, we have encapsulation that is having this public, private, and protected visibility of the classes, right? But again, the emphasis here is more on the inheritance part, and subtyping comes as a byproduct of that, right? Whereas for example, in Smalltalk, the subtyping was the primary interest, and inheritance actually was a secondary interest. You still want to have it, but it's a kind of a balanced thing that you want to have. Yes, subtyping relationship, it's important for me, and that's from my perspective as a user of that object or class. And builder of class can have some something with inheritance, with reuse. Here is a little bit different. So some good decisions about this language. This public, private, protected levels of visibility is kind of interesting, right? So public is visible everywhere, as you know. Protected is within class and subclass declarations. Again, you see that this has something to do with abstraction, but also it has something to do with implementation, right? Implementation of the class. I'm interested in, for example, protected. Protected is actually, I can see things within class, but not outside the class, right? So the subclass derivations, again, from the inheritance perspective, this is kind of putting a different level. So from encapsulation perspective, public and private would have been sufficient, right? But this protected kind of gives you a little bit more flexibility with inheritance, with actual implementation, what you can actually access from your, let's say, from your drive class, right? And friend functions and classes. This is specific to C++, sorry. And this actually shows that a careful attention to visibility and data abstraction is actually is provided here. It's an interesting concept, right? And also it allows inheritance without subtyping. So you don't need to worry about subtyping. As I said, the primary concern is inheritance. This allows actually better control of subtyping than without a private base class, for example. All right. And of course, some problem areas. Otherwise, if it was perfect, it will be probably the dominant object-oriented programming language. You know that it's not the case. There are some other alternatives. So the first problem is with casting. Casting, we are going to talk about this, but as part of multiple inheritance, sometimes you have no operation, sometimes you have you don't have that. And lack of garbage collection, we discussed this. Memory management is error prone. So explicit memory management and also a detailed knowledge of actually what is a heap and what is let's say stack is probably too much. Memory management errors are kind of, let's say, that happens with the constructors. Destructors are helpful, but they are not necessarily, let's say, a solution. But with the newer editions, like with smart pointers and so forth, perhaps you can actually, let's say, overcome some of these difficulties. Objects allocated on stack, again, better efficiency. This is actually used for better efficiency. And interaction with exceptions, this allows, but assignment works badly, especially potentially having a dangling pointer, right? So when you have your objects on stack, and when you lose stack somehow, especially with local variables and so forth, then you have these dangling pointers, possibly dangling pointers, and this is again, you have to be very, very careful. Of course, there are mechanisms to actually limit these error-prone stuff, but that's gonna be your learning curve. Your learning curve is gonna be quite steep in that case. This overloading, there is another concept, we didn't talk about it, but overloading actually is possible, but this actually allows us, or at least this kind of sometimes, let's say, conflicts with the idea of subtyping. And so you have too many different, more than, let's say, enough or more than one code selection mechanism. Okay, this gives you flexibility, of course, but when you have multiple mechanisms, this is against the idea of orthogonality, right? So we want features to be, let's say, just self-contained, and we don't want to repeat those features all over again. And multiple inheritance behavior is quite complex. This emphasis on efficiency and also emphasis on inheritance actually leads to quite complex or complicated behavior. I mean, you know much of these things, so you build a class. Again, this is an extension of a kind of a struct idea of struct. So you have a class, you have overloaded constructors, and you have your virtual functions, and you have your protected things, as well as you have your private things. Virtual functions, these are member functions. A class might have two types of functions, member functions. These are member functions. It could be virtual if explicitly declared or inherited as virtual. So this is gonna be just a simple mechanism. If you declare your member function as virtual, it will be virtual. Otherwise, it will be non-virtual. Okay. So these virtual functions are accessed by indirection through the pointer in the object. So we are going to see this in a few minutes. And it can be redefined in the derived or the subclasses. This is obvious, or you know this one. And non-virtual functions are called in the usual way, meaning through stack. These are just ordinary functions. They are in a symbol table, and they'll be called from that symbol table using kind of these stacks and activation records and so forth. And cannot redefine in a derived classes except of course overloading. You can overload them, but you cannot redefine them in derived classes. So the idea of this is very simple. This says, okay, I know that usual function call in C is very, very efficient. There is very little inefficiency on a call. You just, let's say, copy your values, whatever they are, to your stack, and you actually do your operations within the stack, and you just get out. And then you just release a stack or pop the entries for that thing. And you pay the overhead only when you have a virtual function, where this indirection of finding the code through some pointer mechanism is going to be your, let's say, your cost. The function call is going to be the same, but now you need to find that function, and you are going to be actually just referencing something from a table. Right? So that cost is not actually big. It's not as big as, let's say, what we have in Smalltalk, but even that is actually considered as an inefficiency issue. So what you can do now is, if you don't need to actually inherit, or if you don't need to inherit that function or method somehow, then you just use your regular functions, and it will give you just a little bit of an improvement in the speed. So this balancing actually works quite a bit. Of course, now you have these two different things, and now your programmer needs to know about, okay, when do I actually do a virtual function, and when do I do a regular function? Now, two things can be, I mean, they achieve different things, but they have some overlap, and they are not completely orthogonal to each other. And you have a sample derived class here. You see that, here's my pointer. So you have, this is your base class or superclass, and this is your derived class. And you have your constructors, again, overloaded constructors. You have overloading of the constructors. You can construct this thing in multiple ways. You have your non-virtual function, and you have your virtual functions. Right. And again, protected and your private things as well. Here, of course, you know that this the derivation, you have the other X and Y stuff up there as part of your base class, and you have your new entry as your private entry. So how does this work in the runtime? So you have your point object. Okay, this is again created on stack, right? And you have your you have two things. One is very similar to actually Smalltalk. If you see this one, so you have some sort of a pointer pointing at a table. You can think of this table being similar to dictionary that we had, a method dictionary or a template table that we had in Smalltalk. But it's organized in a different way. It is actually more efficient than that. And you have your let's say instances of your variables and so forth is in your object itself. So this is staying in the stack, and this pointer is actually pointing to a table, and this table will have your code segments here, codes that actually will be chosen as a response to the message that you are going to have. And in the case of color object, you'll have this guy here, and on top of it, you have your new thing, right? So your new variable, local variable, or your instance variable. And then you have now your color, this V table have actually is going to be built up on this one, and it has new entry. This is the code for the, let's say, the color code, right? So now you have this guy. There are two things, and the way that you are going to actually address this, which one to choose is, you see that you don't have the dictionary anymore. It's not a dictionary anymore, meaning I don't know the names of the functions. How am I going to access those? Of course, by just knowing their offset. I'm going to say, okay, if I have this guy, I have only one thing here. If I have this guy, I have two things, and the second function is just actually the second entry in my V table. All right, so very, very simple idea. So just one indirection, you can see that I reach to, for example, this function, this method that I have, I can reach to that function by just one indirection, and then an offset in that direction, right? Whereas in Smalltalk, what we were doing was we had a virtual table here, a dictionary here, and in this dictionary we were checking the name, if the name is there. And then once we find the name, then we will go for the function. If we don't find the name, then we have to go, let's say, somewhere else, right? Okay, and you see here actually the V table, or the code for the let's say the base class function, the virtual function move, is going to be actually in the first entry, and the other one in the second entry, and so forth. So this is how C+ manages the thing compared to this one. As you could see here, we have this. You do one indirection to your class object, and then so this is your object, this is your class object, and then from one indirection to your method dictionary, and you search for your method dictionary. So this is a search. You actually search for each entry for a match, and then you go. If you don't find it, you go up here, and then you actually check for these in that thing. Here you can see that this is quite simplified. So you have just one indirection and then just an offset. So in addition to your, let's say, base pointer here, will actually give you the address of this guy, and you can now take that address and actually run your code at that address.
If you do not put for formal functions in Hafta, it's not going to the base class function.
No, it is already. This is a replica of this guy. These two are the same thing. If it is implemented here, it is actually the same thing. They are the same thing.
Sir, which one is C++, JavaScript? Which one is Smalltalk from these pictures?
This is C++. There is no JavaScript here. This is C++.
Okay.
And this is Smalltalk. I have the JavaScript here, but JavaScript is using similar idea, so that's why I have it here, but don't worry about this one here. So this JavaScript thing, forget about it. I'm comparing to Smalltalk. So this is Smalltalk. This is Smalltalk, and this is C++. Okay. And you can see it in the runtime. You have your objects in your stack, and each of these objects have these V tables, and a single V table, of course, for each class. So class 1 and class 2 has these two V tables, and you have these pointers to these V tables, and then you can access those methods by just knowing which entry in this list of things that you will need to get. All right. And the base class methods are on the top, and derived class, if there are derived class, their methods are going to be on the bottom of that table. So comparing to this one, you have this object will also have another object of this, let's say, color point will also point to this one. You see that, again, you see the complexity of this thing. One indirection, two indirections at least to get to the, let's say, to the its original virtual functions, or a third one, a fourth one to the other one. And again, here you have a search. This is very important. I mean, that search is very expensive. You can actually use very complicated, let's say, nice algorithms like, let's say, KD trees or something like that. But still, it will be quite expensive compared to this one. And memory is also quite efficient here, you see, right? So you have only one V table here, common for the class itself, whereas here you have, again, this one common, and then this one, or this method dictionary, and this method dictionary is actually an overhead. You can see that already. So if you have 640 kilobytes of memory, then you don't want your compiler to, or your, let's say, runtime engine to actually create, let's say, overhead in your memory. So this simplicity of C++ with respect to the lookup simplicity with respect to Smalltalk is Smalltalk has no static type system, right? So it's a dynamic type system. And so this, for example, such a code, object, operation, whatever, could refer to any object, and this is going to be done at runtime. Right? So you need to find a method using the pointer. You start from the pointer, and you move on there. Whereas, so different classes will actually put methods at different places in method dictionary. You have no guarantee of that. Right? Whereas in C++, you actually type gives compiler some superclass, and offset of the data for the function pointer is the same as in subclass and the superclass. So you make sure that your offset is actually the same as in the superclass as well as in the subclass. Again, this is coming from the static typing. And offset data and the function pointer known at compile time. Therefore, you know at compile time where it is going to be. Therefore, you can actually just create code. When you create the code, you can actually just say, okay, take the pointer here, add 5 to that, add 6 to that, and now I have the function, and just call that function. So this p move, for example, will compile a code like this. You take the p of the v pointer, the virtual table pointer, at the first address, because this is the first function, and take this function and pass it to your arguments, and p and x. So this is a simple behavior now. And you can see that there is only one direction here. So there is one indirection here, and then this is actually just an addition operation. So as we say here, I'm getting to this, for example, this one or this one. Move in the case of point or color point is going to be always at the first entry here, V0, V point V0. So I can list them, and compiler can list them. Okay, I have 1, 2, 3, 4, 5 functions, and I know that where they are, and they are only, there is a table that actually keeps the function pointers, and I need to access that thing with only just the first function is the 0th entry, the second function is the first entry, and so forth. And when you will have this one, of course, now I have the same, the V table here is actually just an extension of this guy. You see here, and now still the move function is going to be still the first entry, the 0th entry. So there are some, now we are getting into some details, like, for example, if I have how do I call virtual functions? Right, so if I have two virtual functions here, and in my code, one of these virtual functions calls the other virtual function, and the question is, how does the body of, for example, F call the right G? How does it find actually the right G? All right. In this case, we'll have this simple idea from this pointer or the self from Smalltalk. Code is compiled so that the member function takes an object itself as its first argument. So like this, when this is compiled, this will be this GI, so that it knows actually which virtual function to actually get. All right. So this pointer may be used in member function and can be used to return the pointer to object itself, pass pointer to object itself to another function, and so forth. So this pointer will actually allow us to map these or handle these virtual function calls within virtual functions. Right. So for non-virtual functions, same way as ordinary non-member functions. Compiler generates codes for that function and assigns an address, and an address of code is placed in the symbol table, and whenever you call that function, you go to the symbol table. Of course, we have also overloading, right? So in the case of overloading, we have to remember first that overloading is resolved at compile time, right? This is different from the runtime lookup of virtual functions, so we have to be careful with that. So there is an example here. So we have a parent class with public entries, print class, and void regular class, and also a virtual function, and a child class getting things from parent with public, again, print class and print virtual. And you have the, again, here, okay, what am I trying to share? I don't know what I'm trying to say here, but anyway. So what I'll do is I'll stop here, and let me see, it's 9:25. Yeah, this is fine, 55 minutes. I'll stop here and we'll continue with multiple inheritance on Monday, and we'll continue also, we'll talk about Java as well. I'm hoping to finish it probably on Monday, maybe with another, let's say, 1 hour extension to Wednesday, and we'll be finished with this topic, and we'll start with a new topic maybe at the end of next week or the week after. Any questions?
Sure. I have a question, but it can be a silly question. Can we do, we are doing in overloading, method overloading, re-implementer function, and also we can do in virtual functions. So why we do need virtual functions?
For inheritance. So ask me this question again on Monday, okay?
Okay.
Sorry?
Okay.
All right.